Hello, today we're going to be looking at black holes and we'll be covering issues such as the escape velocity, the Schwarzschild radius, the energy, the mass, the temperature and the entropy, and Hawking radiation. So get yourself a cup of tea and prepare. First, a working definition of a black hole is any body from which the escape velocity, which I'll describe in a moment, is greater than the speed of light. The escape velocity means the velocity you have to travel in order to get away from that body, and if you have to travel at more than the speed of light, then obviously, since nothing can travel at more than the speed of light, including light itself, nothing can get away from that body, so it traps everything, and you can't see it because light can't escape from it. Hence, it is a black body. What do I mean by escape velocity? Well, let's consider the escape velocity of the Earth. Here is the Earth. Here am I, standing on the Earth, and I have a tennis racket in my hand. And my plan is to hit a ball up in the air such that it escapes from the Earth. Now, ordinarily, if I hit a ball up in the air with a certain velocity, it will travel upwards. It will slow down all the time affected by gravity until eventually it stops, and then it will turn round and fall back to the ground again. If I hit it a little harder so that it travels with a greater velocity, then it will go up further, slowing down all the while because of gravity, till eventually it stops, and then it will fall back down to the ground again. Now, I want a situation where I hit the ball up into the air and it never stops. It continues to get out of the Earth's gravitational field, and that is the velocity I need to use to get that to happen is called the escape velocity. So what is the escape velocity for the Earth? Well, we first just need to remind ourselves of two formulae that we've covered in previous videos. The first tells us the force that exists between two masses. Let's say that they are mass capital M and little m. Then the force between those two masses is g, the gravitational constant, times the first mass, capital M, times the second mass, little m, divided by r squared, where r is the distance between them. And strictly, it is the distance between the two centres of the masses, assuming the masses are spherical. We can also remind ourselves that the potential energy that exists is equal to gmm, so it's exactly the same as for the force, but this time it's simply divided by r, not r squared. Now let's consider the Earth, from which the tennis ball is going to escape, and what we're going to say is it's going to travel all the way up here, and it can never stop until it reaches infinity. Of course, it will never reach infinity, but conceptually, if it were to stop before it gets to infinity, then there will be some potential energy, because the potential energy never reduces to zero. It gets smaller and smaller as r increases. R is the distance away from the Earth, but it's never zero. It will only be zero, strictly, when r is infinity. So what we're saying is that the tennis ball leaves the Earth with a certain velocity. It will slow down due to gravity all the way along, but it won't actually stop until it gets to infinity. So at infinity, the velocity will be zero. So the kinetic energy, which is a half mv squared, is also zero because v is zero. And the potential energy is also zero because if there were any potential energy, that would pull the ball back to Earth. So that means that the total energy, which we'll call E total, is the kinetic energy plus the potential energy, and that is zero. Well, energy can be neither created nor destroyed, so the total energy, kinetic energy plus potential energy, has been zero all the way along this particular trajectory. So if you take a point, say roughly halfway, what you can say is that the ball will have a kinetic energy associated with a velocity in that direction, and it will have a potential energy, the scope to pull the ball back to Earth due to its gravitational attraction acting in that direction, and the two are exactly equal, thus making the total energy zero. So what happened right at the beginning when you first hit the ball? Well, when you first hit the ball, it would have a kinetic energy, which is a half mv squared. And that v is the escape velocity. It's the velocity you need to get it, the velocity you need to give it in order for the ball to go all the way to infinity before it stops. It would also have a potential energy, and that potential energy would be g times m, where m is the mass of the Earth, times m, where m is the mass of the tennis ball, divided by r. And r will simply be, for these purposes, the distance between the tennis ball on the surface of the Earth and the centre of the Earth. In other words, it will be the radius of the Earth. And since we've said that at all times these two have to be equal, because the sum of the two is 0, then we have this equation. And we can simply rearrange that to show that v squared is equal to, bring this 2 up here, 2, the m's incidentally cancel, so this now becomes 2gm over r. That's the v squared. And we can calculate that. V squared is equal to 2. Well, g is the gravitational constant, that's 6.67 times 10 to the minus 11. The mass of the Earth is 6 times 10 to the 24 kilograms, divided by the radius of the Earth, which is about 6,400 kilometres, so that's 6.4 times 10 to the 6 metres. Well, let's not be too precise about that. Let's just say that 6.4 and 6.67 broadly cancel out. And then we've got 2 times 6 is 12. And then we've got 10 to the 6 downstairs. You bring that upstairs, it becomes 10 to the minus 6. Times 10 to the minus 11 is 10 to the minus 17. Times 10 to the 24 is 10 to the 7. Or 120 times 10 to the 6. But that's v squared. So v is the square root of that. What's the square root of 120? Well, look, it's about 11. 11 is 121. Let's not worry too much about that. What's the square root of 10 to the 6? It's 10 cubed. So what we're saying is the escape velocity from the Earth is 11 kilometres per second, which is approximately equal to 7 miles per second, which is approximately equal to 25,000 miles per hour. That's the speed you would have to give that tennis ball if it were to escape the clutches of the gravity of the Earth. Now, a professional tennis player probably hits a tennis ball at about 160 miles an hour, so that's a long way short of 25,000 miles an hour, so there's no danger that tennis players will launch their tennis balls into orbit. But you'll also notice that 7 miles a second, which is the escape velocity for the Earth, is a long way short of the speed of light, which is 3 times 10 to the 8 metres a second, or perhaps we should compare this. This is 11,000 metres per second, 11,000. The speed of light is 3 times 10 to the 8, 300 million metres per second. So the escape velocity from the Earth is a long way short of the speed of light. So the Earth is not a black hole, because a black hole needs an escape velocity of greater than the speed of light. So let's just remind you of that formula for escape velocity again. V squared equals 2gm over r, where m is the mass of the Earth. But you'll notice that v squared will get greater as r gets smaller. So if you could take the Earth and squash it, retaining all the mass, you can't get rid of the mass must remain the same, but you just squash the Earth down to a smaller size. How small do you have to make the Earth before the v squared, or the velocity, the escape velocity, becomes equal to the speed of light? Well, let's rearrange this formula, and we get that r is equal to 2gm over v squared. But we are saying that we want the escape velocity to be the speed of light, so that becomes 2gm over c squared. Well, we can work that out. That means that the radius of the Earth, if it were to be a black hole, That means all the mass of the Earth must remain within that new squashed sphere. The radius will be 2 times g, which is 6.67 times 10 to the minus 11, times m, which is, as we said, 6 times 10 to the 24 kilograms, divided by c squared. Well, c is 3 times 10 to the 8, so c squared is 9 times 10 to the 16. Well, very roughly again, 2 times 6 is about 72. 72 divided by 9 is 8. So that's dealt with the numbers. Now we need to deal with the orders of magnitude. Well, 10 to the 16 brought upstairs becomes 10 to the minus 16, times 10 to the minus 11 is 10 to the minus 27. 10 to the minus 27 times 10 to the 24 is 10 to the minus 3. And so we calculate that you'd need to squash the Earth down such that it had a radius of 8 millimeters, and then it would be a black hole. But only if, so we're talking about the size of a marble here, we're talking about a diameter of about 1.6 centimeters. So if you could squash the Earth down to the size of a marble with radius 8 millimeters, retaining all the mass, because you have to do that, retaining all the mass inside that marble, the Earth would become a black hole. Now I want to ask the question, if you could indeed squash the Earth down to a marble whose diameter is 1.6 centimeters, but whose mass is 6 times 10 to the 24 kilograms, in other words, the full mass of the Earth is contained within this marble, if you could do that, would it stay that size? Well, let's think about the ordinary Earth, the Earth before we squash it. And I'm going to put, here's a floorboard on the Earth, and I'm going to put a 1 kilogram weight on that floorboard. And I want to know, what is the force of gravity acting on that 1 kilogram weight? Well, we had the formula before. The formula is gmm over r squared. And in this case, g, of course, is the gravitational constant. We know that. M is the mass of the Earth. That's capital M. Little m is my 1 kilogram weight. And r, let me just move that back, r is the radius of the Earth. It's the distance from the mass to the centre of the Earth. So we can work that out. F is going to be g, which is 6.67 times 10 to the minus 11, times the mass of the Earth, which is 6 times 10 to the 24, times the mass of the 1 kilogram weight, well, that's just 1, divided by r squared. Well, the radius of the Earth, as we've said before, is 6.4 times 10 to the 6 meters. So this is 6.4 times 10 to the 6, all squared, because this is now an r squared term. And we can cancel 6 times 6, cancels with the 6 squared term. Now you've got a 10 to the 6 squared term, which is 10 to the 12. Bring it upstairs, it becomes 10 to the minus 12. 10 to the minus 12 times 10 to the minus 11 is 10 to the minus 23, times 10 to the 24 gives you 10. So the force is going to be 10 newtons. 10 newtons of force acts on the floorboards due to the gravitational attraction. Why then does that 1 kilogram weight not simply fall through the floorboards? Why is it that when I stand on the floorboards, gravity doesn't pull me through them? The answer is that the floorboards are themselves made up of a solid lattice of molecules and atoms, and they are held together by their own atomic and molecular forces, or bonds as they are called, and they actually have a strength. That's what makes a solid a solid. It's because there are bonds between atoms and bonds between molecules that exert a force to hold them together. And those forces are stronger than the 10 Newton force which is applied by gravity to the 1 kilogram weight. So the 1 kilogram weight doesn't fall through the floorboards because the molecular structure of the floorboards is capable of withstanding that. Now, let's suppose you do squash the Earth down to the size of a marble. Here's a floorboard in theory, and there's my 1 kilogram weight. And I now want to ask, what is the force acting on that 1 kilogram weight due to the gravity of the Earth, which is now the size of a marble? Well, exactly the same formula is going to apply. F equals gmm over r squared. And the gmm are not going to change. That means the force is going to be 6.67 times 10 to the minus 11 times the mass of the Earth, which remains the same. We've squashed the same mass into the size of a marble. So that's 6 times 10 to the 24. Times the mass of, this is little m, times the mass of the 1 kilogram weight, which is 1, divided by r squared. But r now is 8 millimeters because we've squashed the Earth down to 8 millimeters. Well, that's 8 times 10 to the minus 3 squared. Now let's see if we can calculate that. We've got 6 times 6 divided by 8 squared. Look, let's just call that a half. We could actually call it 1. That's not going to be of any consequence at all. Now we've got 10 to the minus 3 squared. Well, that's 10 to the minus 6. Bring that up to the top, it becomes 10 to the plus 6. 10 to the 6 times 10 to the 24 is 10 to the 30. 10 to the 30 times 10 to the minus 11 is 10 to the 19 newtons. The force acting on that 1 kilogram mass due to the Earth, if it were the size of a marble, is a half, well, let's forget about that, but 10 to the 19 newtons. 10 billion newtons. The force acting on the Earth when it was the ordinary size was just 10 newtons. And the floorboards were well able to withstand that. But when you get to the Earth crushed to the size of a marble, the force acting on that 1 kilogram weight is 10 billion newtons. And there is no known force to man that can withstand that. Atomic and molecular forces can't. Even the strong and the weak nuclear forces can't. And the electromagnetic force can't. So you now have an irresistible force acting according to the black hole. So consequently, if the black hole were 1.6 centimeters across, gravity would be acting on the outside of that mass, pulling it in. And there would be no force that could stop that from happening. So consequently, if you could squash the Earth down to the size of a marble, it wouldn't stop. It would carry on contracting under its own gravitational force. It would be, as it were, shrunk still further. And nothing could stop it until it reached a dimensionless point, which is called a singularity. And what we say is all the mass of the Earth would then reside in a dimensionless point. It can't have any dimensions. If it has any width at all, the gravity will just pull it in. So it keeps pulling it in until it has no finite dimensions. And that is what's known in mathematical terms as a singularity. There will, however, be a radius around that singularity of 8 millimeters, which says that anything inside that radius has an escape velocity of greater than the speed of light, but anything outside that radius has an escape velocity of less than the speed of light. And that radius is called the Schwarzschild radius. So a black hole will always fall into a singularity because the gravitational attraction on the outer parts of the matter making up the black hole will always be so great that nothing can withstand it. So the black hole must always shrink to a singularity. But there will be a radius around that singularity, inside which the escape velocity is greater than the speed of light, outside which it is less. So the point is that if you travel inside the Schwarzschild radius, you are doomed. You will never be able to escape. but at least outside the Schwarzschild radius there is hope. And I just want to clear up one other point, which is often a point of misunderstanding. If this is the whole uncompressed Earth, the normal sized Earth, with a radius of 6.4 times 10 to the 6 meters, we are not saying, emphatically not saying, that at the centre of the Earth there is a marble-shaped piece of Earth that is a black hole. There is no black hole at the centre of the Earth. Because in order for it to be a black hole, the whole of the mass of the Earth would have to reside inside that marble at the centre. And it clearly doesn't. The mass of the Earth in the shape of a marble at the centre of the Earth would be very small. Only if the whole of the Earth has been squashed into that marble shape at the centre of the Earth would you have a black hole. There is no black hole at the centre of the Earth. So now the question is, how big do black holes have to be? And the answer is they can be any size. They can be ultramassive, and they can be as small as the size of a subatomic particle. But what you have to ask yourself is, how are you going to create a black hole? Because the way we've talked about it so far is to take the Earth and squash it. Well, actually, I don't know how you could do that. So that becomes a rather impractical proposition. We've simply been looking at it theoretically. But suppose instead of this being an Earth, this is a star. And it needs to be a star that is significantly bigger than our Sun. What is happening for the bulk of the time that the star is alive is that gravity is acting on the outer edges of the star, trying to pull it inwards. But that is balanced by the pressure that is created through the nuclear fusion reactions that are happening inside the star, and so consequently the star remains stable. The gravity which is tending to cause it to collapse is balanced by the nuclear fusion which is pushing it outwards. But at the end of the star's life, the nuclear fusion stops, and now there's only gravity. Consequently, the star collapses in on itself. And once again, the question you have to ask is, what's going to stop it? Now, in some cases, it may be that the atomic forces will stop a collapse. In some cases, it may be that the Pauli exclusion principle will stop the collapse. In other words, Pauli says no two electrons can occupy the same state, and that may stop the collapse. In some times, gravity is so great that it just knocks Pauli's exclusion principle for 6. All the electrons and all the protons are squashed together to become neutrons, and then you get what's called a neutron star. It's very much smaller. It contained principally of neutrons, and the neutron forces can withstand the pressure of gravity. But if the star is massive enough, nothing can withstand the gravitational collapse, and consequently the star collapses to a dimensionless point, and that is a black hole. So that is one mechanism for creating a black hole, but in theory any mass could become a black hole provided there is a mechanism for getting that mass to live within its Schwarzschild radius, effectively to become a dimensionless point. Now let's ask the question, does a black hole therefore suck everything into it? Is everything in its vicinity doomed? Well, the answer is no. Let's consider just the ordinary Earth. Here is the ordinary Earth, and here is the Moon. And the Moon, of course, as we know, orbits the Earth. And the reason it orbits the Earth, at least as far as Newtonian mechanics is concerned, is because the Earth exerts a force on the Moon, which is gmm over r squared, and that force provides the centripetal force that keeps the Moon in orbit, and the centripetal force is mv squared over r. So that's what's keeping the Moon in orbit, and r is the distance between the centre of the Earth and the centre of the Moon. Now suppose the Earth were suddenly, by some mechanism, to become a black hole. So it just becomes a black hole with all its mass residing in a dimensionless point. As far as the moon is concerned, it doesn't care. The G, M and M remain the same. The mass of the Earth is still capital M. It's just that it's now all in a dimensionless point at the centre. R squared remains the same. The distance between the moon and that centre, that singularity, remains the same. So the moon just carries on orbiting the Earth, which has become a black hole. There is now no greater gravitational force because these features remain the same. So consequently, the moon wouldn't care if the Earth became a black hole. It would simply continue to orbit it. This, incidentally, is a feature of what's called Gauss's law. Gauss's law says, and this applies both in electrostatics and also electromagnetism and also in gravity, that when you're talking about the effect of a mass, it doesn't matter whether that mass is a spherical mass or all the mass is residing in a single point, the singularity. As long as you're outside the sphere, as long as you're here, you mustn't be there, as long as you're outside the sphere, then this formula applies. It doesn't care whether M is a spherical mass or a singularity. The same conditions apply. That's a feature of Gauss's law. But of course we can ask the question, what happens if you've got something like a meteor heading towards the Earth? Well, what it would have done when the Earth was the normal size, what it would have done, here's the meteor coming towards the Earth. Let's forget about the atmosphere of the Earth. Probably the meteor would burn up in the atmosphere, but let's forget the atmosphere. It would just continue to accelerate under the force of gravity until eventually it hit the Earth. And depending on how big it is, there might be an explosion. Well, suppose that the Earth has become a black hole. And the black hole, of course, will have a Schwarzschild radius around it. All that now will happen is that the meteor will continue to be attracted. It will cross the Schwarzschild radius, where in theory nothing particularly happens, although in a moment I'll explain something might, and it crashes into the singularity, and it is absorbed, and consequently the black hole increases its mass by any material or energy that hits it. So for example, the cosmic microwave background radiation, which is coming from all directions, will hit the black hole. It cannot be re-emitted, so consequently the black hole increases in energy due to the cosmic microwave background radiation, and any other space debris that happens to be passing by and is stupid enough to get caught will fall into the black hole. Now, I said that you could pass the Schwarzschild radius and nothing particularly happens. Well, actually that's not quite true. It rather depends. Remember, the gravitational forces at this point are going to be massive. You remember we calculated the gravitational force of a black hole the size of the Earth on a 1 kilogram weight was some of the order of 10 billion newtons. So there's a massive gravitational attraction. That's not the problem. The point is that there will be what's called very high tidal forces. So the difference between the gravitational attraction at the Schwarzschild radius and say 6 feet above the Schwarzschild radius will be huge. And so if you were falling into the black hole, the gravitational attraction, and you were falling feet first, the gravitational attraction on your feet when you got to the Schwarzschild radius would be 10 to the 19 newtons, but the gravitational attraction on your head, here you are falling in feet first, the gravitational attraction on your feet is going to be huge. The gravitational attraction on your head is going to be significantly less, and the consequence is you're just going to get stretched out of all existence. You will be torn apart as you cross the Schwarzschild radius, if not before. For the next part of this video, I want to forget about black holes just for a moment, because I want to remind you about features of space-time. You remember that we draw space-time as time and space. Now space, of course, has 3 dimensions: up and down, side to side, back and forth. but I can't easily draw 3 dimensions of space and 1 dimension of time. So I'm simply going to, for simplicity, draw 1 dimension of time, because there is only one, and 1 dimension of space. We'll forget about the other 2 dimensions. This is a 1-dimensional space. And remember that the principle of space-time is that if you stand still in space, you still move through space-time because time is moving. So if you're standing still in space, you won't move in this direction, but standing still in space will result in you doing that, because you are moving forward in time. When we draw a space-time diagram, conventionally, we draw the speed of light at an angle of 45 degrees. So that represents the speed of light. That is, light travelling at a distance in a certain time. So this is 3 times 10 to the 8 metres per second. Consequently, I think you'll agree and understand that it is quite impossible for you to travel like that in space-time, because that implies that you have travelled a distance in space, but in no time at all. You have travelled at infinite speed, and that's impossible. Special theory of relativity says you can't go more than the speed of light. So consequently, motion in space-time must be at an angle of greater than 45 degrees. That is possible, that is not, because that would suggest you're going greater than the speed of light, that suggests you're going less than the speed of light. This line, remember, says you're not travelling at all in space, but you are travelling in time. And of course you'll also agree, won't you, that it's impossible to do that in space-time, because that implies you're going backwards in time. Okay, so now let's think of space-time, and we're going to consider an accelerating object in space-time. So first of all, let's just draw our space-time coordinates, time and space. And we'll start here at 0 velocity, and we're going to accelerate away. And we've seen in previous videos that the shape of an acceleration is something like that. It just means that for every second that goes by, you travel faster, and therefore you travel further. So consequently, this curve is produced. That is the curve of an accelerating body. Constant acceleration, but of course continually increasing velocity, means that you cover a lot more ground in the same amount of time. But in a space-time chart, we've already said that you can never travel at an angle of less than 45 degrees. So once you've got to, and here is the angle of 45 degrees is about here, the acceleration does not allow you to do that. So strictly, if we're going to draw a proper space-time chart, because you're not allowed by special relativity to go at greater than the speed of light, if that's the speed of light, and you start out here accelerating, what you actually do is to asymptotically approach that line. But you'll never get to it. That's the point. You never get to it. Well, you do when you reach infinity, but not before. So you accelerate, you get progressively faster, but you never reach the speed of light. You continue to get faster and faster by infinitesimal amounts, and you're asymptotically approaching the speed of light. And this curve here, I could, for example, draw the other side of it. This curve is called a hyperbola. This is a hyperbolic function, and it shows how you would accelerate in space-time. Of course, we're talking about acceleration that is getting you up to close to the speed of light. Ordinarily, if you accelerate on a motorway, you probably can do this, but of course the acceleration would not take you anywhere near the speed of light. But when you're accelerating such that you're getting close to the speed of light, that's when you get asymptotically closer to the speed of light, and your acceleration curve becomes a hyperbola. Okay, so let's draw the space-time chart again. And this time we're going to imagine that we've got, there's the speed of light, there is the acceleration which is a hyperbola and asymptotically approaches the speed of light. And we're going to consider this is a rocket, and the rocket contains Alice and Bob. It's always Alice and Bob. And when the rocket gets to this point here, Bob is going to do something very ungallant. He's going to actually put Alice outside the rocket. The rocket is accelerating constantly, and that's its path through space-time. But of course, as soon as Alice is put outside the rocket, she has no longer got any separate propulsion. She's got no force. Newton's first law kicks in, and she will simply continue to travel at the velocity she was travelling when she was put outside the rocket by Bob. And since the velocity she was travelling in is that direction, she will proceed through space-time now in a straight line, travelling at a constant velocity. Now, can Alice, this is Alice travelling, and this is Bob still in the rocket, can Alice see Bob? And I'm talking about visual communication, or any other form, frankly, of electromagnetic radiation. She can communicate by radar waves if you wish. Well, remember that the speed of light can only travel at 45 degrees, so it can either go in that direction or it can travel in that direction. Those are the only options that you've got for light travelling through space-time according to the rules that we have set about the speed of light. So yeah, Alice has no problem seeing Bob because light from Bob travelling at the 45 degree mark will continue to reach her wherever she is. So what she's actually seeing, of course, what this space-time diagram is telling you is that she sees Bob getting progressively further away, represented by the increasing length of these lines. And that's perfectly fair. What has effectively happened is that Bob has dropped her off, travelling at 30 miles an hour, whilst he accelerates away. Consequently, she will always see him getting further and further away. That's fine. What does Bob see when he looks for Alice? Well, I think the first thing you can recognise is that once Alice crosses this point here, in other words, once she crosses this line which represents the speed of light, Bob will never be able to see her. Why? Because light which leaves Alice from this point on can never get back to Bob. To do so, it would need to travel at an angle that's less than 45 degrees, and that means it would have to travel at more than the speed of light. And light travels at the speed of light. So light from Alice goes like that, like that, like that, like that, like that. But it's never going to reach Bob, because Bob is always on this side of the speed of light line, whereas the light coming from Alice, which can go in either direction, of course, it can go that way at 45 degrees or this way at 45 degrees, never gets to Bob. So you might conclude from that that what Bob will see, I mean, it's okay when Alice is here, Bob can see her then because light from Alice will indeed reach Bob. But you might think that what Bob will see is Alice drifting towards this point here and then disappearing from view. But that's not actually what happens. I'm just going to blow up this particular part of the diagram. So what we've actually got is, here is Alice's trajectory, here is the speed of light, and here is Bob's trajectory. What will actually happen is that light from Alice will reach Bob, travelling at 45 degrees, you know, the speed of light. But it will take an increasingly long time for that light to reach Bob because Bob is travelling further and further away. And remember, he's going very fast. He's almost going at the speed of light. So light itself is going to take a long time to catch him up. It will do because the light is travelling at the speed of light and Bob is travelling at slightly less than the speed of light. But this is just going to continually go like this. And what is actually going to happen is that Bob, looking back, will perceive that Alice is travelling slower and slower towards this point here, but never crossing it. Now that is just a pure perception. In fact, what will happen, of course, is that Alice, travelling at the velocity she was travelling when she was dumped off the rocket or the spacecraft, will just continue to go through that line and carry on, no problem. But Bob's perception is quite different. He perceives that she goes slower and slower and slower and slower and slower and slower and slower, but never crosses that line. It's the difference between reality and perception. And the reason I went through all of that, we can now go back to black holes, is that that is exactly what happens. Here's a black hole, a dimensionless singularity. Here's the Schwarzschild radius around it. That is the radius, remember. Within that radius, the escape velocity is greater than the speed of light. Outside, it's less. If you've got somebody travelling towards the black hole to certain doom, and you've got somebody observing from the outside, but safe, maybe they're in orbit around the black hole, so they're safe, the people travelling towards the black hole simply recognise that they are accelerating, they're getting faster and faster and faster until eventually they hit the black hole and calamity. But the observer observing those people will actually see the same kind of phenomena as Bob. What they will see is the rocket getting slower and slower and slower and slower and slower and slower and never actually reaching the Schwarzschild radius. So actually it's a bit of a false hope, because the observer thinks that they haven't yet met their doom and there's still time to save them. The reality is they have long since crashed into the black hole and been completely annihilated. And the reason for this is that the gravitational forces here are so strong that light is having an enormous difficulty travelling away, and consequently the observer simply sees this spacecraft apparently taking longer and longer and longer and travelling slower and slower and slower to get to the Schwarzschild radius, but never crossing it. And there is a mathematical equation which demonstrates this. Just to remind you, from special relativity, we have shown that there is an invariant quantity called the proper time. The point about special relativity is it says that all observers, if they are measuring a particular distance or they're measuring a particular time, depending on their relative velocities, they will measure different distances and different times. So nobody agrees on the measurements. But there is a quantity called proper time, which everybody can agree on. And the way you can calculate proper time is to say that c squared, which is the speed of light, times tau squared, where tau is the so-called proper time, the time that everybody can agree on, is equal to c squared t squared, which is the time that any observer measures, minus x squared, where x is the distance that anybody measures. So if you measure a time and a distance, and somebody else measures a time and a distance, then they will get different answers. But if you plug it into this formula, both parties will get the same tau. That's just from special relativity, and you can see my videos on special relativity for more information about that. But I do it to show that there is a similarity to this new equation which I'm going to show you, which is called the Schwarzschild metric. And that is derived from Einstein's field equations, and one day I will work out a way of explaining that with sufficient simplicity that I can do it in the style that I like. But basically what the Schwarzschild metric says is that c squared tau squared is, and I should say this now has to be done in polar coordinates, so we're instead of using x, y and z Cartesian coordinates, we use ordinary Cartesian coordinates, we use r, theta and phi, and it becomes 1 minus rs over r, where rs is the Schwarzschild radius, times c squared t squared, minus r squared over 1 minus rs over r, minus r squared d omega squared, where d omega is just a shorthand. It's a combination of thetas and phis, which I don't need to go into now because that's not going to be relevant to what I'm going to show you. But you can see a kind of similarity with this term and this term. You've got c squared tau squared in both. You've got a c squared t squared. You've got an r squared instead of an x squared, but that's because we're using polar coordinates. But you've got this peculiar term here, 1 minus rs over r. And we said that rs is 2mg over c squared. That is the formula for the Schwarzschild radius that we calculated earlier in this video. So now you can see that two things happen. There are peculiar things happening. When r is equal to rs, this term becomes 0 because rs over rs is 1 and 1 minus 1 is 0. You also get funny things happening when r itself is 0, in other words, when you hit the black hole. When you hit the black hole, rs divided by 0 becomes infinity. And so you've got an infinity term here, you've also got an infinity term here, and effectively the whole thing blows up. The singularity is not one that obeys the Schwarzschild metric anymore. Indeed, the whole point about a singularity is that the laws of physics generally don't apply anymore. But there's also the interesting question of what happens when r is rs, in other words, when you are at the Schwarzschild radius. In those circumstances, rs over r is 1, 1 minus 1 is 0. 0 times c squared t squared is 0, minus r squared over 1 minus rs over r. Well, 1 minus rs over r is 0, because we are at the Schwarzschild radius, so r equals rs. So this term blows up to infinity. And you can forget about that one for these purposes. And what that is showing is, remember, proper time is the time that is read by the person travelling. So if you are travelling in the rocket, or in the rocket that's run out of fuel, if you are travelling in that rocket heading towards the black hole to your certain doom, and you've got a clock inside that rocket with you, proper time is the time you measure on the clock, because you're travelling with the clock. The times that other people measure are the times that they observe of you. And what this formula essentially is showing is that for an infinitesimally small amount of time on the rocket, when the proper time as measured by the person on the clock on the rocket is an infinitesimally small amount of time, the time measured by the observer will be infinite. And that's why the rocket appears to travel ever slower, ever slower, ever slower, without ever crossing the Schwarzschild metric, because what is actually happening is that the observer is seeing the rocket over a very brief instant of time, but that instant of time appears to be an infinity of time. In practice, the rocket, of course, has accelerated, accelerated, accelerated and smashed into the black hole. But the observer, according to this metric here, will see time expand enormously. So that in fact what seems to be a fraction of a second on the rocket becomes an eternity of time for the observer. And that's why they never see them cross the Schwarzschild metric, the Schwarzschild radius. I now want to look at the energy and entropy of a black hole. So there is the dimensionless black hole, and there is the Schwarzschild radius around it. And I want to add 1 unit of energy to the black hole. So what I'm going to do is I'm going to allow 1 photon to fall into the black hole. And we know that the energy of a photon, we've done this many times before, is h nu, where nu is the frequency of the light of which the photon is a part, and that is the same as hc over lambda. H is Planck's constant, and we've done this in many other videos. Now, if we assume that the wavelength of the light is of the order of the Schwarzschild radius, which it needs to be. If lambda is very much bigger than the Schwarzschild radius, then the light might just pass it by with never ever seeing it. But if lambda is broadly of the order of the Schwarzschild radius, then you can have this situation. We take the famous Einstein formula E equals mc squared, which means that a change in mass is equal to a change in energy divided by c squared. That just comes from this formula here. But delta E, well, we can say for one photon, delta E is hc over lambda. So that's hc over lambda, that's delta E, times c squared. And the c cancels, so that now becomes h over lambda c. So that is the change in mass as a consequence of one photon falling into the black hole. Now we have said that lambda is Rs, and we know that Rs is equal to 2mg over c squared because we calculated that earlier in this video. And if we take this formula here and ask, how does the radius vary according to increasing mass, then you would simply say that delta R, an increase in radius, will equal 2 delta mg over c squared. Because that just falls out of that. A small increase in mass leads to a small increase in the Schwarzschild radius. But we can substitute for delta m here what we calculated here with lambda equal Rs. So now we can say that delta R is equal to, well, 2g over c squared times delta m, which is h over lambda c, but lambda we're going to say is comparable to the Schwarzschild radius. That's 2g, not 29, up here. And if I bring that Rs term up here, I get that Rs delta R is equal to 2g divided by c squared times h over c from here. I've just brought that Rs term up on this side of the equation. And that's 2gh over c cubed. And that's a constant. Whoops, sorry. 2gh over c cubed is a constant. Now, the surface area associated with the Schwarzschild radius is going to be 4 pi times the Schwarzschild radius squared, because that is the surface area of a sphere. And if I take dA by dr, that is just going to be 8 pi rs, because you're differentiating with respect to r, you get 8 pi rs. And that means that dA is equal to 8 pi rs dr, just multiplying by dr. But we know what rs dr is because we calculated that up here. So now we can substitute that dA is equal to 8 pi times rs dr, which is 2gh over c cubed. And that, if you like, is saying that the area increases by an amount dA as a consequence of putting one photon of energy, also one element of entropy, because we'll regard a photon as being the basic unit of entropy, and that is that formula. If you put in several units of entropy, several photons, then the increase in the surface area will be 8 pi 2gh over c cubed times ds, where ds is the amount of entropy. And if we rearrange this formula, we get that, and now have S and A, we now get that S is equal to AC cubed divided by a set of constants times GH. In other words, we're going to take the 16 pi and just make it a constant. And that is known as the Bekenstein formula. It shows you how the entropy of the black hole changes as its area increases. That's the area of the surface area associated with the Schwarzschild radius. We can also consider the temperature of the black hole. In our thermodynamics video, we derived the idea that the change in energy is equal to the temperature times the change in entropy. Now, for one photon of energy, we have said above that the change in energy is hc over lambda. That was what we derived, right? Well, we didn't derive it, we stated it because we've derived it in, or shown it in other videos. So the change in energy from one photon is hc over lambda. So now we can say that for one photon, where ds essentially is 1, because we're saying one photon is 1 unit of entropy, so for one photon we've got that dE equals T, because ds is 1, and dE is also hc over lambda. But remember, we're also saying that lambda is broadly of the order of the Schwarzschild radius, so that's hc over rs, and rs is 2mg over c squared, so that's hc over 2mg over c squared. And you can see that h and c and c squared and g are all constants, which means that you now have that t is proportional to 1 over m. The only variable in this term here is the mass m. So this is an interesting and surprising result, that as the mass of the black hole increases, its temperature decreases. And as the mass decreases, the temperature increases. So a small black hole will be hotter than a big black hole. That's contrary to usual concepts, because we reckon that as mass increases, energy increases, because E equals mc squared, so an increasing mass equals increasing energy. And of course, we usually associate increasing energy with increasing temperature. But black holes, it's quite the reverse. And finally, Professor Stephen Hawking has proposed that black holes could lose energy, and indeed in some circumstances evaporate away by radiating out energy. And you might say, how can that possibly be, given that we've just spent most of this video showing that once material or radiation gets into a black hole, it can never escape because the escape velocity is greater than the speed of light. So how can anything ever get away from a black hole? And the answer is that it actually doesn't. The principle is all based on what's called quantum fluctuations. The argument is that in space where you have nothing, from absolutely nothing at all, where energy is nothing, quantum fluctuations allow particle pairs to be created, usually matter and antimatter. They then recombine and take you back to energy is nothing. So the books balance. You start with nothing, you end up with nothing. Ordinarily you would say nothing comes from nothing. But in quantum mechanics that's not true. From nothing, something can appear as long as the books balance and you go back to nothingness again. You certainly can't create energy out of nothing, but for a short time you get these quantum fluctuations where things materialize and then dematerialize. It's a fundamental principle of quantum mechanics. Now, suppose that happens. Here is my black hole, it's the singularity, and here's the Schwarzschild radius around the singularity. And suppose a quantum fluctuation happens here, outside the Schwarzschild radius, and two particles appear, matter and antimatter. And this particle flies off in this direction, and this particle flies off in this direction. Now, if this is capable of escaping, because it's outside the Schwarzschild radius, so there's a theoretical possibility that it can escape, the two will never re-meet in order to annihilate. Consequently, the argument goes that the universe, which is the universe out here, has got additional energy from this particle. From absolutely nothing, this particle was created together with this particle. If this particle survives and goes off into the wider universe has gained energy. The books must balance, so this particle must effectively represent negative energy. And negative energy going into the black hole will reduce the amount of energy of the black hole. Consequently, you can have a situation where the black hole will evaporate because it is getting negative energy and therefore reduction in its total energy. In practical terms, of course, if you take massive black holes, that doesn't happen because the amount of material going into the black hole, the cosmic microwave background radiation, the debris of space that may be attracted to the black hole, that input into the black hole, here's the black hole with all the material going into it, radiation and matter, which is adding to the mass of the black hole. Against that, you've got some fairly feeble reductions in the energy in the black hole due to this process of pair production as a result of quantum fluctuations outside the Schwarzschild radiation, outside the Schwarzschild radius. The evaporation is nowhere near as great as the amount of material coming in, so the net effect is the black hole just continues to grow. But if you have a very, very small black hole, that could evaporate away almost instantaneously. And that's possibly the reason we don't see small black holes, because the capacity for them to evaporate is very high and they just disappear altogether. And that is a brief introduction to black holes. E is the gravitational constant, that's 6.67 times 10 to the minus 11. The mass of the Earth is 6 times 10 to the 24 kilograms, divided by the radius of the Earth, which is about 6,400 kilometers, so that's 6.4 times 10 to the 6 meters. Well, let's not be too precise about that. Let's just say that 6.4 and 6.67 broadly cancel out. And then we've got 2 times 6 is 12. And then we've got 10 to the 6 downstairs. You bring that upstairs, it becomes 10 to the minus 6. Times 10 to the minus 11 is 10 to the minus 17. Times 10 to the 24 is 10 to the 7. Or 120 times 10 to the 6. But that's v squared. So v is the square root of that. What's the square root of 120? Well, look, it's about 11. 11 is 121. Let's not worry too much about that. What's the square root of 10 to the 6? It's 10 cubed. So what we're saying is the escape velocity from the Earth is 11 kilometers per second, which is approximately equal to 7 miles per second, which is approximately equal to 25,000 miles per hour. That's the speed you would have to give that tennis ball if it were to escape the clutches of the gravity of the Earth. Now, the scope to pull the ball back to Earth due to its gravitational attraction acting in that direction, and the two are exactly equal, thus making the total energy 0. So what happened right at the beginning when you first hit the ball? Well, when you first hit the ball, it would have a kinetic energy, which is a half mv squared. And that v is the escape velocity. It's the velocity you need to get it, the velocity you need to give it in order for the ball to go all the way to infinity before it stops. It would also have a potential energy, and that potential energy would be g times m, where m is the mass of the Earth, times m, where m is the mass of the tennis ball, divided by r. And r will simply be, for these purposes, the distance between the tennis ball on the surface of the Earth and the centre of the Earth. In other words, it will be the radius of the Earth. And since we've said that at all times these two have to be equal, because the sum of the two is 0, then we have this equation. And we can simply rearrange that to show that v squared is equal to, bring this 2 up here, 2, the m's incidentally cancel, so this now becomes 2gm over r. That's the v squared. And we can calculate that. V squared is equal to 2. Well, Hello, today we're going to be looking at black holes, and we'll be covering issues such as the escape velocity, the Schwarzschild radius, the energy, the mass, the temperature and the entropy, and Hawking radiation. So, get yourself a cup of tea and prepare. First, a working definition of a black hole is any body from which the escape velocity, which I'll describe in a moment, is greater than the speed of light. The escape velocity means the velocity you have to travel in order to get away from that body, and if you have to travel at more than the speed of light, then obviously, since nothing can travel at more than the speed of light, including light itself, nothing can get away from that body, so it traps everything, and you can't see it because light can't escape from it. Hence, it is a black body. What do I mean by escape velocity? Well, let's consider the escape velocity of the Earth. Here is the Earth. Here am I, standing on the Earth, and I have a tennis racket in my hand. And my plan is to hit a ball up in the air such that it escapes from the Earth. Now, ordinarily, if I hit a ball up in the air with a certain velocity, it will travel upwards. It will slow down all the time, affected by gravity, until eventually it stops, and then it will turn round and fall back to the ground again. If I hit it a little harder so that it travels till it reaches infinity, of course it will never reach infinity, but conceptually, if it were to stop before it gets to infinity, then there will be some potential energy, because the potential energy never reduces to zero. It gets smaller and smaller as r increases. R is the distance away from the Earth. But it's never zero. It will only be zero, strictly, when r is infinity. So what we're saying is that the tennis ball leaves the Earth with a certain velocity. It will slow down due to gravity all the way along, but it won't actually stop until it gets to infinity. So at infinity, the velocity will be zero. So the kinetic energy, which is a half mv squared, is also zero because v is zero. And the potential energy is also zero because if there were any potential energy, that would pull the ball back to Earth. So that means that the total energy, which we'll call E total, is the kinetic energy plus the potential energy, and that is zero. Well, energy can be neither created nor destroyed, so the total energy, kinetic energy plus potential energy, has been zero all the way along this particular trajectory. So if you take a point, say roughly halfway, what you can say is that the ball will have a kinetic energy associated with a velocity in that direction, and it will have a potential energy with a greater velocity. Then it will go up further, slowing down all the while because of gravity, till eventually it stops, and then it will fall back down to the ground again. Now, I want a situation where I hit the ball up into the air and it never stops. It continues to get out of the Earth's gravitational field, and that is the velocity I need to use to get that to happen is called the escape velocity. So what is the escape velocity for the Earth? Well, we first just need to remind ourselves of two formulae that we've covered in previous videos. The first tells us the force that exists between two masses. Let's say that they are mass capital M and little m. Then the force between those two masses is g, the gravitational constant, times the first mass, capital M, times the second mass, little m, divided by r squared, where r is the distance between them. And strictly, it is the distance between the two centres of the masses, assuming the masses are spherical. We can also remind ourselves that the potential energy that exists is equal to gmm, so it's exactly the same as for the force, but this time it's simply divided by r, not r squared. Now let's consider the Earth, from which the tennis ball is going to escape. And what we're going to say is it's going to travel all the way up here, and it can never stop until